Hello, dear wanderers of the night. Welcome back to the Midnight Explorer, where we journey together through the quieter corners of knowledge, where stories unfold like stars appearing one by one in the darkening sky. Tonight, I want to take you somewhere vast, somewhere silent, somewhere that exists at the very edge of what we can know and what we can only imagine. Tonight, we're going to talk about black holes. But this isn't a story of cold mathematics or distant abstractions. No, this is a story about humanity reaching into the darkness and finding something that would change everything we thought we knew about existence itself. This is a story about the people who dared to imagine the impossible, who stared into the void and asked, "What if?" So settle in. Dim your lights. Let the world outside fade away for a little while, because tonight we're going to explore the silent monsters of space. A question written in starlight. It's a summer evening in 1783. The air is warm, thick with the scent of English gardens. In a modest study in the countryside, a man sits by candlelight, quill in hand, thinking about something impossible. His name is John Mitchell. He's a country rector, a man of God, but also a man consumed by questions about the universe. Tonight he's wondering about something strange, something that won't let him sleep. What if a star could be so massive, so impossibly heavy, that not even light could escape it? It seems absurd. Light is the fastest thing in the universe. Light streams from the sun, crosses the void, and reaches us in mere minutes. Light fills our days, our eyes, our world. How could anything trap light? But Mitchell knows something. He knows that Einstein's laws suggest that light might have mass, might be affected by gravity, and if that's true, well, then perhaps there could exist a star so dense, so crushing in its gravitational pull, that even light, speeding away at its incredible velocity, would be pulled back down, would fall, would be trapped. He writes this down. In elegant, measured prose, he describes what he calls a dark star. A celestial body from which no light can escape. A place in space that would be invisible, present but unseen, felt but never glimpsed. It's a beautiful thought, a haunting thought, but it's only a thought, a mathematical curiosity scratched onto parchment by candlelight. The world isn't ready for dark stars yet. But let's pause here for a moment, you and I. Let's sit with John Mitchell in his study, the candle burning low, the night pressing against the windows. Let's feel what he felt. Because what Mitchell discovered that night was something profound, that the universe might contain mysteries so deep, so strange, that they defy our everyday experience. That there might be things out there that we cannot see, cannot touch, cannot directly know, but that are nonetheless real. This is the beginning of our story. This is where humanity first glimpsed the possibility of black holes, though we wouldn't call them that for nearly 200 years. And like all great stories, this one begins with a question asked in the darkness. The universe expands, and so do our questions. For more than a century, Mitchell's dark stars remained a footnote in the history of astronomy, an interesting idea, a mathematical oddity, but nothing more. The world moved on. The 1800s brought new telescopes, new ways of seeing. Astronomers mapped the heavens with increasing precision. They measured the distances to stars, cataloged nebulae, discovered new planets orbiting our sun. The universe grew larger with each passing decade. And then came Albert Einstein. It's 1915. The world is at war. Europe is tearing itself apart in trenches and battlefields. But in Berlin, In a quiet office far from the guns, a man with wild hair and kind eyes is completing what will become his masterpiece. He calls it general relativity. It's not an easy theory to understand. Even Einstein himself struggled with its implications. But at its heart, it says something beautifully simple. Gravity is not a force. Gravity is the shape of space itself. Imagine, if you will, a stretched piece of fabric, a trampoline perhaps. Now place a bowling ball in the center. The fabric curves, bends, sinks down around the weight. If you roll a marble across this fabric, it won't travel in a straight line. It will curve, following the shape created by the bowling ball. This, Einstein said, is what mass does to space. The sun creates a curve in the fabric of space-time, and the Earth follows that curve, orbiting not because it's pulled by an invisible force, but because it's following the natural contours of bent space. It's beautiful, it's elegant, and it's provably true. But it also opens up new questions, stranger questions, that even Einstein didn't want to face. One of the first people to truly understand Einstein's equations was a young German physicist serving on the Russian front during World War I. His name was Karl Schwarzschild. Picture him, it's 1915, he's in the trenches, surrounded by the horror of war. Men dying, cold, mud, fear. And yet somehow, in stolen moments between the chaos, Schwarzschild is thinking about Einstein's equations. He's working through the mathematics in his head, on scraps of paper, whenever he can. And he discovers something. He discovers that Einstein's equations predict a point, a boundary, beyond which the curvature of space-time becomes infinite. A place where space curves so sharply that it folds in on itself, where time itself stops making sense. He calls this boundary the Schwarzschild radius. Today, we know it by a more dramatic name, the event horizon. Schwarzschild sends his solution to Einstein from the front lines. Einstein is amazed. He presents the work to the Prussian Academy of Sciences. But even as he does, Einstein feels uneasy. The mathematics works, the solution is correct, but it describes something that seems impossible, something that shouldn't exist. Karl Schwarzschild never sees the impact of his work. He dies of a disease contracted in the trenches just a few months later, at the age of 42. But his legacy lives on. His equations, his boundary, his glimpse into the impossible. The event horizon. Let's sit with that idea for a moment. The event horizon. Imagine standing on the shore of an ocean. The water stretches out before you, vast and deep. Now imagine that somewhere out there, beyond where you can see, there's a line in the water. And if you cross that line, you can never come back. The currents beyond it are too strong. They pull you inexorably towards something you cannot see, cannot escape. That's an event horizon. For a black hole, it's not water that pulls you. It's space itself. Cross that invisible boundary and space is flowing toward the center so quickly that even moving at the speed of light, you could never swim back upstream. You could never return. It's a one-way door, a threshold forever. And for decades, most physicists believed such things were purely mathematical constructs, interesting on paper, impossible in reality. When giants fall. To understand black holes, we need to understand stars. And to understand stars, we need to understand something profound about the universe. Everything is trying to collapse. Think about that for a moment. The natural state of matter is to pull together, to fall inward, to compress. Gravity never stops. It never rests. It's always pulling, always drawing things closer. So why doesn't the sun collapse? The answer is beautiful in its simplicity. The sun is exploding. Deep in its core, hydrogen atoms are being crushed together with such force that they fuse into helium. This fusion releases tremendous energy, heat, light, radiation, and this energy pushes outward, creating pressure that holds the star up against the inexorable pull of its own gravity. It's a balance, a dance, gravity pulling in, nuclear fire pushing out, and in that balance, stars live. Our sun has been dancing this dance for 4.6 billion years. It will continue for billions more. But eventually, the dance must end. Eventually, the fuel runs out. It's the 1930s now. The world has moved from one war into the shadow of another. In Cambridge, a brilliant young Indian physicist named Subrahmanian Chandrasekhar is thinking about what happens when stars die. He knows that when a star like our sun exhausts its fuel, it will collapse, but it won't collapse completely. The electrons in the star's matter will resist being crushed together, a quantum mechanical effect called electron degeneracy pressure. The star will compress down to about the size of Earth, becoming what we call a white dwarf. Still hot, still glowing, but supported by the strange quantum properties of matter itself. But Chandrasekhar discovers something unsettling. He calculates that there's a limit. If a star is more than about 1.4 times the mass of our sun, electron degeneracy pressure isn't enough. The gravity is too strong. The star will keep collapsing. This limit, now called the Chandrasekhar limit, is a fundamental boundary in the universe. It's the point at which quantum mechanics loses its battle with gravity. When Chandrasekhar presents his findings to the Royal Astronomical Society in 1935, he's met with skepticism, even ridicule. The great Arthur Eddington, one of the most respected astronomers of the age, publicly dismisses the idea. He says nature would never allow something so absurd. But Chandrasekhar is right, and nature, it turns out, is far stranger than even our brightest minds can easily accept. Collapse into darkness. So what happens when a massive star, much more massive than our sun, runs out of fuel? Picture it. For millions of years, this star has been a titan. Massive, brilliant, pouring light into the cosmos. Its core has been a furnace, fusing hydrogen into helium, helium into carbon, carbon into heavier elements. Each stage of fusion releases energy, holding the star up against gravity's relentless pull. But there is a problem. Each stage produces less energy than the last, and eventually, the star begins fusing silicon into iron. And iron is where the music stops. Iron doesn't release energy when it fuses. It takes energy. Iron is the end of the line. So the core suddenly has no pressure to hold it up. And gravity has been waiting for millions of years. And now, in less than a second, the entire core collapses. It falls inward faster than sound can travel through it. The core, which was roughly the size of Earth, compresses to the size of a city, then smaller. The electrons are crushed into the protons, forming neutrons. The matter becomes so dense that a teaspoon of it would weigh as much as a mountain. And then it rebounds. The collapse is so violent that it creates a shock wave that blows the outer layers of the star into space. We see this from Earth as a supernova, one of the brightest events in the universe. For a few weeks, a single dying star can outshine an entire galaxy. But what's left behind? If the core is more than about 3 times the mass of our sun, another limit, another boundary, even the pressure from neutrons isn't enough to stop the collapse. There's no force in nature that can hold it up. So it keeps falling. It falls past the size of a city, past the size of a mountain,
It falls through its own Schwarzschild radius, through its own event horizon, and becomes something new, a black hole. Let's pause and feel the weight of that moment. The birth of a black hole. This is matter giving up. This is the universe reaching a point where all the forces we know, all the properties of space and time that seem so solid and real, simply break down. The collapsing core falls out of our universe in a sense. It creates a wound in space-time, a place where our physics stops making sense. And around it, like a scar, is the event horizon. The boundary between what can be and what is lost forever. It's violent, it's catastrophic, and it's happening somewhere in the universe right now. And now. And now. Stars are dying. Black holes are being born. And for decades, we could only theorize about them. We could only write the equations and wonder. Because how do you see something that gives off no light?
Listening to the invisible. It's the 1960s. The world is changing rapidly. Humanity has entered the space age. We've launched satellites, put people in orbit, set our sights on the moon. And we've developed new ways of seeing the universe. X-ray astronomy is born. Scientists realize that some of the most energetic, violent processes in the universe emit X-rays. And these X-rays can be detected by instruments on satellites above Earth's atmosphere. In 1964, a team launches a rocket carrying X-ray detectors. The mission lasts only a few minutes before falling back to Earth, but in those minutes, they detect something extraordinary. A source of X-rays in the constellation Cygnus. They call it Cygnus X1. At first, no one knows what it is, but as more observations accumulate, a picture begins to emerge. Cygnus X1 is part of a binary system, two objects orbiting each other. One is a visible blue supergiant star. The other is invisible, but it's clearly there. You can see its gravitational effects on the supergiant. You can calculate its mass. And the mass is too high to be a white dwarf, too high to be a neutron star. Slowly, carefully, scientists begin to suggest the impossible. Cygnus X1 might be a black hole. But how can you prove something exists when you can't see it? The answer lies in the X-rays. You see, even though black holes themselves don't emit light, they don't exist in isolation. In a binary system like Cygnus X1, the black hole is pulling matter away from its companion star. This matter doesn't fall straight in. It spirals, forming what we call an accretion disk, a swirling disk of gas and dust orbiting the black hole, getting faster and hotter as it gets closer to the event horizon. As this matter spirals inward, friction heats it to millions of degrees, and at those temperatures, it emits X-rays, brilliant, powerful X-rays. So even though we can't see the black hole itself, we can see the light from the matter about to fall in. We can see the last screams of doomed gas and dust as they circle the drain. It's like seeing a whirlpool by watching the leaves spinning on its surface. You never see the center, but you know it's there. A portrait emerges. Through the 1970s and 80s, more candidates for black holes are found. Each one is invisible. Each one reveals itself only through its effects on nearby matter, through the X-rays, through the gravitational dance of companion stars. Scientists develop theories. They calculate what black holes should look like, or rather, what the space around them should look like. They predict that if you could somehow see one up close,
you'd see light bending in strange ways. You'd see the photon sphere, a region where light can actually orbit the black hole. You'd see gravitational lensing, where light from stars behind the black hole gets bent around it, creating multiple distorted images. You'd see, just outside the event horizon, a dark circle, a shadow, the absence of light defining the presence of something terrible and magnificent. But these are just predictions, just mathematics, beautiful, precise, but untested. Because black holes are far away, very far away. And even though they're enormous by human standards, they're tiny compared to the distances involved. Seeing the shadow of a black hole would be like standing in New York and trying to see a grape in Los Angeles. It's impossible. Or so everyone thought.
The heart of a galaxy is an amazing place, filled with billions of stars, nebulae, black holes. But it's also dangerous. Plummeting into the center of our galaxy would be a harrowing experience. Let's talk about physical dangers first. The orbits of stars near the center of the galaxy are highly elliptical. They're a lot more crowded than stars out in our galaxy's neighborhood. There are also stronger magnetic fields and more energetic radiation than your average corner of the galaxy. But what should concern you most of all is the massive black hole at the very center. In the 1970s, astronomers start noticing something strange at the center of our galaxy. Our galaxy, the Milky Way, is a spiral. Hundreds of billions of stars arranged in graceful arms, rotating around a common center. And at that center, 26,000 light-years away, hidden behind vast clouds of dust and gas, something is happening. Radio telescopes detect a bright source of radio waves at the galactic center. They call it Sagittarius A star, pronounced Sagittarius A star. For years, no one knows what it is. But in the 1990s, two teams of astronomers, one led by Andrea Ghez in California, another by Reinhard Genzel in Germany, began a patient, methodical study. They use infrared telescopes, which can peer through the dust. They photograph the center of the galaxy, and then they wait. A year passes. They photograph it again. The stars near the center have moved. Another year, another set of photographs, more movement. Year after year, they track individual stars orbiting something at the galactic center. And as the years accumulate, they can calculate orbits. They can determine what those stars are orbiting around. What they discover is staggering. There's an object at the center of our galaxy with a mass of about 4 million times that of our Sun, and it occupies a space smaller than the orbit of Mercury around our Sun. The only thing that can be that massive and that compact is a black hole, a supermassive black hole. And it's not alone. As telescopes improve, as surveys extend to other galaxies, a pattern emerges. Almost every large galaxy has a supermassive black hole at its center, millions, even billions times the mass of our Sun, sitting there, waiting. These aren't the black holes formed from dying stars. These are something else, something older, something that may have helped shape the galaxies themselves as they formed in the early universe. We still don't fully understand how they got so big, how they formed, whether they grew by consuming matter over billions of years, or whether they were somehow born massive in the chaotic early universe. But they're there, at the center of most galaxies, including ours. We live in a galaxy with a monster at its heart. Dancing with giants. Let's think about what this means for a moment. Right now, as you listen to this, there is a black hole at the center of our galaxy. It's so massive that if you replaced our Sun with it,
its event horizon would extend almost to Mercury's orbit. It's so massive that its gravity influences the motion of stars hundreds of light years away. And yet, we're safe. We orbit the galaxy at a comfortable distance. The black hole's gravity is strong at its location, but it spreads out, weakens with distance, just like the gravity of any other massive object. Black holes aren't cosmic vacuum cleaners. They don't suck everything in. They have gravity, certainly, but so does everything with mass. If you replace the sun with a black hole of the same mass, Earth would continue orbiting exactly as it does now. We'd freeze in the darkness, yes, but we wouldn't be pulled in. You have to get close for things to get really strange, really dangerous. And one star has gotten very close. It's called S2, or sometimes SO2, depending on which team named it first. It's a blue star, bright and massive, and it orbits Sagittarius A star in a stretched ellipse. Every 16 years, S2 completes one orbit, and at its closest approach, it screams past the black hole at about 3% the speed of light. That's thousands of kilometers per second. It passes within about 17 light hours of the event horizon, roughly 4 times the distance from the Sun to Neptune. Astronomers have watched it complete multiple orbits now. They've measured how its light gets redshifted, stretched to longer wavelengths, as it climbs out of the black hole's gravitational well. They've measured the subtle ways its orbit is affected by the curvature of space-time itself. And every measurement confirms Einstein's predictions. General relativity holds up even in this extreme environment, even in the presence of a supermassive black hole. But S2 is still far from the event horizon. It's dancing at the edge, but never falling in. What would it be like to go closer, to approach the point of no return?
Approaching the horizon. Let's imagine a journey. You and I, somehow protected in an impossible spacecraft, approaching a black hole. It's not a supermassive black hole like Sagittarius A asterisk. Those are so large that you could cross the event horizon and not even notice for hours. Instead, let's approach a stellar mass black hole, one formed from a collapsed star. 10 times the mass of the Sun, with an event horizon about 30 kilometers across. We start far away, where space-time is still fairly flat, where things still make sense. The black hole is invisible ahead of us, but we can see the light from stars behind it being bent, lensed. We can see the shadow, a dark circle blocking out the background light. As we get closer, strange things start to happen. First, we notice that the stars around us are shifting. Light from stars behind us is getting bent around the black hole, appearing in front of us. We start to see more and more of the sky compressed into a smaller and smaller area directly ahead. Meanwhile, the darkness, the shadow of the event horizon, grows larger. If we had a companion ship far away, watching us, they would see us start to slow down. Not because our engines are failing, but because time itself is passing more slowly for us than for them. This is gravitational time dilation. The closer we get to the black hole, the more slowly our clocks tick compared to the outside universe. To us, everything feels normal. But to them, we're moving in slow motion. Our radio signals are getting stretched, red-shifted, coming in slower and slower. We cross what's called the photon sphere, the region where light can orbit the black hole. If we looked around, we could theoretically see the back of our own ship, light having traveled in a complete circle around the black hole before reaching our eyes. But we don't linger. We're still falling, still approaching the event horizon. And here's where things get truly strange. If we look ahead
toward the black hole, we see the event horizon now taking up half our view, a perfect circle of absolute blackness. But if we look behind us, we see everything. We see the entire future of the universe, compressed and blue-shifted, because the light falling into the black hole with us includes light from all future times, all compressed into the final moments before we cross the horizon. Time has become strange here. Space has become strange. The normal rules are bending, warping, preparing to break. Crossing over. And then we cross the event horizon. Nothing dramatic happens. No flash of light, no barrier, no sensation at all. The event horizon is just a mathematical surface, a point of no return. But locally, right at that moment, space-time seems normal. Except we can't go back, no matter what we do. No matter how powerful our engines, we could point our ship straight up, away from the singularity at the center of the black hole, and fire our thrusters at maximum, but we wouldn't move away. We'd still be falling inward. Because inside the event horizon, all paths lead to the center. Inward isn't a direction you can resist anymore. It's built into the structure of space-time itself. It's like trying to travel backward in time. You can't choose to do it because the flow of time has a direction. Similarly, inside the event horizon, the flow of space has a direction toward the singularity. And something else is happening, something we'd rather not experience. The gravity at our feet is stronger than the gravity at our head, much stronger. This difference, this tidal force, is stretching us, pulling us longer and thinner. There's a term for this, coined by physicists with a dark human sense of humor: spaghettification. For a small black hole like the one we're approaching, these tidal forces would tear us apart, long before we reached the center. Atom by atom, molecule by molecule, we'd be stretched into a thin stream of particles. For a supermassive black hole, you could actually cross the event horizon intact and survive for hours more before reaching regions where the tidal forces become lethal. But either way, the ending is the same. We fall toward the singularity. What is the singularity? According to Einstein's equations, it's a point of infinite density at the center of every black hole. All the mass that collapsed to form the black hole, all the matter that has fallen in since, is compressed to a single point with zero volume and infinite density. But this is where our physics breaks down, where our equations give us infinities, and infinities means we don't really understand what's happening. Most physicists believe the singularity isn't really infinite. They believe that when we develop a theory of quantum gravity, a theory that unites Einstein's general relativity with quantum mechanics, the infinities will resolve into something finite, but still incredibly strange. Perhaps the matter is compressed to the Planck length, the smallest possible meaningful distance in physics. Perhaps space-time itself has a texture, a foam-like quality at these scales that prevents true infinite compression. But we don't know. We can't know because we can't see inside a black hole. The event horizon hides the singularity from the rest of the universe. This is called cosmic censorship. The idea that nature never allows a naked singularity, a singularity not hidden behind an event horizon, to exist. It's as if the universe is maintaining its own modesty, hiding its points of breakdown from view. Let's float here for a moment, you and I, in this impossible space. Let's think about what it means. A singularity is a place where our understanding ends, where the map of reality has an edge marked, "Here be dragons." It's humbling. It reminds us that for all our advances, for all our telescopes and equations, there are still mysteries so deep that we can only point at them and wonder. And yet there's something almost poetic about it. These places of ultimate mystery are sealed away, hidden behind event horizons, as if the universe is protecting us from confronting the truly incomprehensible. Or perhaps protecting itself.
Ripples in the fabric. It's September 14, 2015. In 2 locations in the United States, one in Louisiana, one in Washington State, incredibly sensitive instruments are listening to the universe. These instruments are called LIGO detectors, Laser Interferometer Gravitational Wave Observatory. Each one consists of 2 tunnels, each 4 kilometers long, arranged in an L shape. Laser light bounces back and forth down these tunnels, and incredibly precise instruments measure the light's travel time. Why? Because Einstein predicted something else. He predicted that when massive objects accelerate, they create ripples in space-time itself, gravitational waves. These waves stretch and compress space as they pass through, but by almost imperceptibly small amounts. LIGO was built to detect these ripples, to feel the universe vibrating. And on that September morning, at 5:51 a.m. Eastern Time, both detectors feel something. A chirp, a signal lasting a fraction of a second, starting at a low frequency and rapidly rising in pitch, growing louder, then suddenly stopping. The scientists reviewing the data can hardly believe it. The signal is clear, strong, and it matches exactly what Einstein's equations predict should happen when 2 black holes spiral into each other and merge. 2 black holes, each about 30 times the mass of the Sun, had been orbiting each other for perhaps millions or billions of years. Slowly, over time, they lost energy by radiating gravitational waves, and their orbit decayed. They spiraled closer and closer together. In the final moments, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. The space around them was churning, twisting, radiating energy. And then they collided. They merged into a single black hole. And in that collision, in that merger, 3 solar masses worth of energy, the equivalent of 3 suns completely converted to pure energy, was released in the form of gravitational waves. For that brief moment, the collision radiated more power than all the stars in the observable universe combined. And 1.3 billion years later, a tiny fraction of that energy reached Earth. The ripples passed through the planet, compressing and stretching space by less than 1,000th the diameter of a proton. But it was enough. LIGO felt it. Humanity heard, for the first time, the sound of colliding black holes. Let's think about what this means. For the first time in history, we detected something not through light, not through electromagnetic radiation of any kind, but through the ripples in space-time itself. We felt the universe vibrate. Black holes, the most silent objects in existence, had spoken, and we had learned to listen. Since that first detection, LIGO and other gravitational wave detectors have sensed dozens of black hole mergers. We're now regularly hearing these cosmic collisions. We're beginning to build a census of black holes in the universe. We're learning how common they are, how they form, how they evolve. We're listening to the universe in a completely new way. And the universe, it turns out, is louder than we thought. The shadows made visible. But there was still one image we hadn't captured, one thing we hadn't seen. We detected black holes through X-rays, through the motion of nearby stars, through gravitational waves. But we'd never actually photographed one, never seen the shadow that theory predicted should be there. In 2017, an international team of scientists embarked on an ambitious project.
They called it the Event Horizon Telescope. The idea was audacious. Use radio telescopes scattered across the entire Earth, from Hawaii to Chile to Spain to the South Pole, and combine their data to create, in effect, a single telescope as large as planet Earth. This would give them the resolution needed to see the shadow of a black hole's event horizon. But which black hole to target? Sagittarius A star at the center of our galaxy was an obvious candidate, but it's relatively small and variable with hot gas swirling around it chaotically. The other target was M87 star, the supermassive black hole at the center of the galaxy M87. This galaxy is much farther away, about 55 million light-years, but its black hole is enormous, 6.5 billion times the mass of our Sun, one of the most massive black holes we know. They decided to observe both. For several nights in April 2017, the telescopes around the world turned to the sky and collected data. Enormous amounts of data. So much data that it couldn't be transmitted over the internet. It had to be physically shipped on hard drives to a central processing facility. Then began the painstaking work of combining the data, of calibration, of processing, of building an image from interferometric radio data collected from around the globe. It took 2 years. And then on April 10th, 2019, the team held a press conference. Simultaneously, in multiple cities around the world, they revealed an image. An orange ring, bright on one side, dimmer on the other. And in the center, darkness. Perfect darkness. The shadow of the event horizon of M87 star. Let's pause and look at that image together. In our minds. It's fuzzy. It's not a crystal clear photograph, but it's real. It's an actual image of a black hole, or rather of the region around a black hole. The bright ring is light from gas swirling around the black hole at nearly the speed of light. The gas on the side moving towards us is brighter, Doppler boosted. The gas moving away is dimmer. And in the center, the shadow. Larger than the event horizon itself because the black hole's gravity bends light around it, but unmistakable, undeniable. For the first time in history, we had visual proof. Black holes are real. The event horizon is real. Einstein was right. The image went viral. It appeared on news sites, social media, t-shirts, coffee mugs. For a few days, the whole world was thinking about black holes, about the universe, about the incredible achievement of seeing something that was supposed to be invisible. In 2022, the Event Horizon Telescope team released a second image, this time of Sagittarius A star, the black hole at the center of our galaxy, our black hole, the one we orbit around along with hundreds of billions of stars. And there it was, smaller than M87 star, more difficult to image because of its variability, but there nonetheless. Another ring of light, another shadow. We had seen the monster at the heart of our own galaxy.
Where does information go? But photographing a black hole doesn't mean we understand them. In fact, the more we learn, the more questions emerge. One of the deepest questions involves something physicists call the information paradox. Here's the problem. According to quantum mechanics, information cannot be destroyed. If you know the state of a system at one time, and you know the laws of physics, you can, in principle, calculate the state of that system at any other time, past or future. Information is preserved. But black holes seem to destroy information. Anything that falls past the event horizon is lost forever, cut off from the rest of the universe. The matter falls to the singularity, and then what? The information about that matter, about its quantum state, seems to disappear. This creates a contradiction between general relativity and quantum mechanics. And physicists hate contradictions.
They mean something is wrong, something is missing from our understanding. Stephen Hawking made this paradox even worse in 1974 when he discovered that black holes aren't completely black. Let me tell you about Stephen Hawking. He was a young physicist at Cambridge, brilliant and ambitious, when he was diagnosed with ALS, a degenerative disease that would gradually rob him of movement, of speech, of almost everything except his mind. But what a mind! In the early 1970s, Hawking was thinking about quantum mechanics and black holes. Classical physics said that nothing could escape a black hole, but quantum mechanics introduces uncertainty, strange effects at tiny scales. Hawking realized that if you think about the quantum vacuum, the apparently empty space that's actually seething with virtual particles constantly popping into and out of existence, something strange should happen near an event horizon. Normally, these virtual particles appear in pairs, a particle and an antiparticle, and immediately annihilate each other. But near the event horizon, one particle might fall in while the other escapes. To an outside observer, it would look like the black hole is radiating particles. This is called Hawking radiation. The implications are profound. If black holes radiate, they lose energy. And since Einstein told us that mass and energy are equivalent, losing energy means losing mass, which means black holes can evaporate. For large black holes, this process is incredibly slow. The black hole at the center of our galaxy would take 10 to the 100 years to evaporate, a number so vast it's almost meaningless. The universe is only 13.8 billion years old. We could write the age of the universe a trillion times over and not approach that number. But small black holes, if they exist, could evaporate faster. And when a black hole gets small enough, it should evaporate completely in a final burst of radiation. And here's the problem. What happens to all the information that fell into the black hole? If the black hole completely evaporates, leaving only random thermal radiation, then that information has been destroyed. The information paradox. Physicists have been arguing about this for 50 years. Hawking himself proposed several solutions over his lifetime, changing his mind more than once. Some physicists believe the information is somehow encoded in the Hawking radiation. Others think it might be stored at the event horizon, in subtle correlations we don't yet understand. There are theories involving black hole complementarity, the idea that information appears to be destroyed to someone falling in, but is preserved to someone watching from outside, and somehow both perspectives are valid. There are theories involving firewalls, energetic barriers at the event horizon that destroy anything trying to cross. There are theories involving connections to other universes, to baby universes being born inside black holes. We don't know which, if any, are correct. This is still an active area of research, still a mystery. And perhaps that's as it should be. Perhaps black holes should keep some secrets. Time and tide. Let's return to the journey we imagined earlier, approaching a black hole. But this time, let's think more carefully about what happens to time. Imagine you have a twin. You're going to approach the black hole while your twin stays far away, safe and sound. You promise to fall in and report back somehow. As you approach the event horizon, your twin watches through a telescope. At first, everything seems normal. But as you get closer, they notice something strange. You seem to be slowing down. Your movements become sluggish. Your radio signals arrive further and further apart. From your perspective, nothing has changed. You feel normal. Your clock is ticking normally. But from your twin's perspective, time is slowing down for you. You get closer and closer to the event horizon. To your twin, watching from far away, you seem to slow down more and more. You never quite reach the horizon. You freeze there, your image getting dimmer and redder as your light gets stretched to longer and longer wavelengths. Eventually, you fade from view entirely. But to your twin, you never cross the event horizon. You're frozen there forever, asymptotically approaching but never reaching the boundary. But from your perspective, something completely different happens. You sail right through the event horizon, no hesitation, no freezing. It takes only a few seconds, perhaps, from your point of view. Both perspectives are real. Both are correct. This is the strange nature of relativity. What happens depends on where you are, how you're moving, how deep you are in a gravitational field. To the outside universe, nothing ever quite falls into a black hole. It just gets frozen at the event horizon, slowly radiating its information back out over unimaginable timescales. But from the perspective of that matter itself, it fell through long ago. It's gone. Which perspective is real? Both. Neither. The question itself might not make sense in a universe where time and space are relative, where reality depends on your reference frame. Black holes don't just bend space. They bend our understanding of existence itself.
When black holes collide. We've talked about individual black holes, but black holes don't always exist alone. Sometimes they find each other, and when they do, they dance. Imagine two black holes, each the collapsed core of a massive star, born perhaps in the same stellar nursery millions of years ago. Their parent stars lived and died relatively close to each other, and now the two black holes orbit each other, a binary system bound by gravity. At first, their orbit is wide. They circle each other leisurely, taking years or centuries to complete a single orbit. They're far enough apart that space-time around them, while curved, isn't doing anything too exotic. But they're radiating gravitational waves, constantly, quietly. These waves carry energy away from the system, and as energy is lost, the orbit decays. The black holes spiral slowly inward. This happens over vast timescales. For millions of years, perhaps billions, the black holes draw closer. The decay is imperceptible at first, but gravity is patient. As they get closer, the orbital period decreases. What took years now takes months, then weeks, then days. And now the gravitational waves are getting stronger. Space-time around the black holes is no longer gently curved. It's churning, roiling, twisted into complex shapes by the two masses whipping around each other. Hours, minutes, seconds. In the final moments, the black holes are orbiting each other hundreds of times per second. The gravitational waves are screaming through space, ripples carrying enormous energy. The black holes themselves are moving at significant fractions of the speed of light. Space-time is being twisted into shapes we can barely describe mathematically. The event horizons are no longer spherical. They're stretched, distorted, reaching toward each other. And then they touch. The event horizons merge. For a brief moment, there's a strange, complex shape. Not quite two separate black holes, not quite one. The singularities spiral around each other inside a common event horizon. The space around them radiates energy furiously. In that final fraction of a second, the power output in gravitational waves exceeds the light output of all the stars in the observable universe combined. And then it's over. The singularities merge. The event horizon settles down into a sphere, slightly larger, slightly more massive than either of the original black holes, but smaller than the two combined. The missing mass has been converted to energy, radiated away as gravitational waves. A new black hole is born from the death of two others. And the gravitational waves spread out across the universe at the speed of light, carrying the news of this cosmic collision to any civilization capable of listening. Supermassive encounters. What we've just described happens with stellar mass black holes. But what about the supermassive black holes at the centers of galaxies? Galaxies collide. It's not uncommon. The universe is vast, but it's also been around for 13.8 billion years, and gravity is always pulling, always drawing things together. When two galaxies collide, it's not like cars crashing. The stars are so far apart that they mostly pass through each other like ghosts. But the galaxies as a whole merge, their gas and dust mixing, triggering bursts of star formation. And the supermassive black holes at their centers? They sink toward the middle of the merged galaxy. They form a binary system, just like the stellar mass black holes, but on a vastly larger scale.
Two black holes, each millions or billions of times the mass of the Sun, orbiting each other. We found systems like this. Galaxies in the process of merging, with two bright active galactic nuclei indicating two supermassive black holes dancing around each other. These systems are rare enough that we haven't yet detected the gravitational waves from supermassive black hole mergers. The waves from such events are too low in frequency for LIGO to detect. They require space-based detectors or pulsar timing arrays. But we're building those detectors, we're setting up those arrays, and soon we'll hear these mergers too. Imagine the gravitational waves from 2 billion solar mass black holes spiraling together. Waves with wavelengths measured in light years. Waves that would make the entire galaxy vibrate slightly as they pass through. It's happening somewhere in the universe right now. A dance of titans, a merger of monsters. And someday soon, we'll hear it.
Quasars and the violent universe. Let's talk about what happens when black holes eat. Most of the time, supermassive black holes at galaxy centers are quiet. They're not actively consuming much matter. They sit there, massive and patient, their presence felt through the orbits of nearby stars, but otherwise relatively inactive. But sometimes something falls in. A star wanders too close. A cloud of gas is funneled inward. Perhaps a whole other galaxy has merged, sending vast quantities of matter spiraling toward the center. And then, the black hole begins to feed. Remember the accretion disk we talked about earlier? The disk of material spiraling into the black hole, heated by friction until it glows? For a supermassive black hole that's actively feeding, this accretion disk can be enormous, light years across, containing matter equivalent to millions of stars. And it's hot. Millions of degrees hot. This hot disk doesn't just glow, it blazes. It can outshine the entire rest of the galaxy. We call these objects quasars, quasi-stellar radio sources. From far away, they look like stars, but they're actually the brilliant accretion disks around feeding supermassive black holes billions of light years away. The brightest quasars are the brightest objects in the universe. A single quasar can be 100 times brighter than an entire galaxy. But that's not all. Some of the material in the accretion disk doesn't fall into the black hole. Instead, it gets ejected, channeled somehow along the black hole's rotation axis, accelerated to nearly the speed of light, and shot out into space in two enormous jets. These jets can extend for hundreds of thousands of light years. They're made of plasma, superheated gas and particles, moving so fast that relativistic effects become important. Time dilates for the particles in these jets. Space contracts in their direction of motion. When these jets slam into the gas between galaxies, they create enormous lobes of radio emission. Some of these lobes are bigger than entire galaxy clusters. Black holes, in other words, don't just affect their immediate surroundings. A feeding supermassive black hole can influence its entire galaxy, perhaps even its entire galaxy cluster. The energy pumped out by the accretion disk and jets can heat the surrounding gas, preventing it from cooling and forming new stars. Black holes might regulate galaxy growth. They might be one of the key factors determining how galaxies evolve. The tidal disruption. Sometimes a star makes a terrible mistake. It wanders too close to a supermassive black hole. If the star stays outside a certain distance, the tidal radius, it's fine. It can orbit the black hole safely, like S2 orbiting Sagittarius A star. But if it crosses the tidal radius, something dramatic happens. The gravitational pull on the near side of the star becomes significantly stronger than the pull on the far side. The star gets stretched, pulled apart. This is called a tidal disruption event. Imagine being that star for a moment.
You've existed for millions or billions of years, steadily fusing hydrogen in your core, steadily pouring light into space. You've perhaps had planets, maybe even, somewhere in your history, planets with life. And now, you're approaching something you can't see, can't fully comprehend. The gravity gets stronger, strange. Your outer layers begin to feel stress. And then, over the course of hours or days, you are torn apart. Your matter streams away from your former self in long tendrils. Some of it escapes, flung back into space by the encounter, but most of it falls into an orbit around the black hole, forming an accretion disk. Over the following weeks and months, this disk heats up and begins to glow. From far away, observers see a galaxy suddenly brighten, a new source of light where none existed before. It peaks in brightness, then slowly fades over months or years as the disk is consumed by the black hole. We've observed dozens of these tidal disruption events now. Each one is the death certificate of a star, the obituary written in X-rays and ultraviolet light. Each one is a reminder that space, for all its beauty, is also a place of violence, of destruction on scales we can barely conceive.
Wormholes and possibilities. Einstein's equations allow for other strange solutions beyond black holes. One of the most famous is the wormhole. Imagine space-time not as a flat sheet, but as a three-dimensional structure that can curve and fold. Now imagine two black holes, far apart in space. But what if their interiors connect? What if there's a tunnel, a shortcut through space-time linking them? This is a wormhole, also called an Einstein-Rosen bridge. Mathematically, they're allowed. The equations don't forbid them. But physically, almost certainly impossible. The problem is stability. Even if a wormhole could form, it would immediately collapse unless it was somehow held open. And the only thing that could hold it open, according to our equations, is something with negative energy density. Exotic matter that repels rather than attracts. We've never found anything with negative energy density. Quantum mechanics allows for small temporary regions of negative energy, but nothing that could hold open a macroscopic wormhole. So wormholes remain a beautiful mathematical curiosity, a science fiction dream, probably impossible. But, and this is important, we can't be absolutely certain. Our understanding of extreme gravity is still incomplete. Our theory of quantum gravity doesn't exist yet. There might be loopholes we haven't discovered. The universe has surprised us before. White holes and time reversal. Here's another strange solution to Einstein's equations: white holes. A black hole is a region you can enter but never leave. A white hole would be the opposite, a region you can leave but never enter. Matter would pour out of a white hole, but nothing could go in. They would be black holes running backward in time. Do they exist? Almost certainly not. We've never seen anything that remotely resembles a white hole. And there's no obvious mechanism for how they could form. Black holes form from collapsing matter. There's a process, a history, but white holes would need to exist from the beginning of the universe, or form through some process we don't understand. Most physicists consider them purely theoretical. Interesting mathematical solutions, but not physical reality. But, again, we can't be absolutely certain. The universe is under no obligation to be simple or intuitive. The multiverse connection. Some theories suggest that black holes might be connected to other universes. That the singularity at the center of a black hole might be the Big Bang of another universe budding off from our own. In this view, our own universe might have been born inside a black hole in a parent universe, and every black hole in our universe might contain entire universes of its own, with their own laws of physics, their own stars and galaxies, their own civilizations perhaps wondering about black holes.
Universes within universes, nested like Russian dolls, extending infinitely in both directions. It's a beautiful idea. Poetic. But is it true? We don't know. We might never know. These baby universes, if they exist, are completely cut off from us by the event horizon. We can't send signals into them, we can't receive signals from them. They're fundamentally unobservable. Which raises a philosophical question. If something is completely unobservable in principle, with no possible way to test it even indirectly, is it science or is it metaphysics? Physicists disagree on this. Some think such ideas are legitimate physics as long as they fall out of otherwise testable theories. Others think we should stick to what we can observe. Both views have merit, and the debate continues. The long dark. Let's think about the future, the deep future, the far, far future. Right now, the universe is 13.8 billion years old. That sounds ancient. It's hard to even conceive of that much time. But compared to how long the universe will exist, 13.8 billion years is nothing. We're living in the early universe, the infant universe. Stars are still being born, galaxies are still colliding, merging, creating new structures. The universe is vibrant, active, alive. But this won't last forever. In about 1 trillion years, give or take, the last new stars will form. By then, most of the hydrogen gas in galaxies will have been used up or ejected. Star formation will cease. The stars that exist will continue burning for a while. Small red dwarfs can live for trillions of years, but eventually even they will exhaust their fuel. One by one, the stars will go out. In 10 to the 14 years, 100 trillion years, the universe will be dark. No more stars, no more light. Just the slowly cooling remnants, white dwarfs, neutron stars, black holes. And even these won't last forever. White dwarfs and neutron stars will cool, eventually reaching the background temperature of the universe. They'll become black dwarfs and black neutron stars, cold, dark, essentially inert. But even matter itself may not be stable over these timescales. Protons might decay. It's never been observed, but some theories predict that given enough time, perhaps 10 to the 36 years, even protons will fall apart into lighter particles and radiation. If that happens, the white dwarfs and neutron stars will slowly evaporate. Atom by atom, they'll dissolve into radiation. And what will be left? Black holes. Only black holes. For a long time, an incredibly long time, the universe will consist of nothing but black holes of various sizes, slowly evaporating through Hawking radiation. The last light. Remember that Hawking radiation gets faster as a black hole gets smaller? Larger black holes evaporate slower. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. That's a 1 followed by 67 zeros, an incomprehensibly long time. The supermassive black holes at galaxy centers, they'll take 10 to the 100 years, maybe longer. But eventually, they'll evaporate too. Slowly, over time scales that make the current age of the universe seem like an eye blink, the black holes will shrink. They'll radiate their mass, they'll get smaller and smaller, and in their final moments, as they reach microscopic sizes, they'll evaporate rapidly, explosively. Each black hole will end in a final burst of radiation, a last flash of light in the darkness. And then, nothing. In 10 to the 100 years, or perhaps longer, the last black hole will evaporate, the last flash will fade, and the universe will be empty, dark, cold, just the faint background of radiation stretched by the expansion of the universe into ever longer wavelengths. The heat death of the universe. Let's sit with that image for a moment. A universe with no structure, no complexity, no information. Just uniform, cold emptiness expanding forever. It's a melancholy thought. But there's something strangely beautiful about it too. The universe will have lived a full life. It will have created stars, galaxies, planets, perhaps life and consciousness scattered across billions of worlds. It will have explored every possible structure, every possible form of complexity allowed by the laws of physics. And then, having exhausted all possibilities, it will rest. Black holes in this view are the last guardians, the final repositories of structure and information. They'll outlive everything else. They'll be the universe's memory, holding on to the patterns of all that ever was for unimaginable stretches of time. And when they finally fade, when the last black hole evaporates, it will be like the universe forgetting its own history, like the final pages of the last book being burned. A sad ending, but an ending nonetheless.
What we've learned. Let's gather our thoughts. Let's look back on this journey we've taken together through the darkness. We started with John Michell in 1783, wondering about dark stars by candlelight. We followed the thread through Einstein's general relativity, through Schwarzschild's solution, through Chandrasekhar's limit. We learned how stars die, how they collapse, how they create these wounds in spacetime that we call black holes. We learned about the event horizon, the point of no return, about spaghettification and singularities, about how time becomes strange near a black hole, how perspectives diverge. We listened to black holes collide, heard the ripples they make in space-time itself. We saw their shadows, those photographs that seemed impossible just a few years ago. We watched them feed, creating the brightest objects in the universe. We imagined them dancing, merging, growing. We considered the paradoxes they create, the questions they raise about information and reality and the limits of knowledge. And we glimpsed the far future, when black holes will be all that remains, the last structures standing before the final darkness. But here's the thing. For all we've learned, black holes remain mysterious. We still don't know what happens at the singularity. We still don't know how to reconcile quantum mechanics with general relativity in these extreme conditions. We still don't know if information is truly preserved or destroyed. We still don't fully understand how supermassive black holes grew so large so quickly in the early universe. We've solved some puzzles, but each solution reveals new questions, deeper questions, stranger questions. And I think that's beautiful. The value of the unknown. We live in an age that often fears uncertainty. We want answers. We want to know everything. We get anxious when we encounter questions we can't answer. But black holes remind us that mystery is not a flaw in our understanding, it's a fundamental feature of reality. There are things that are genuinely difficult to know, things that might be impossible to know, at least from our perspective outside event horizons. And that's okay. The existence of mysteries doesn't mean we should stop seeking answers. The scientists who detected gravitational waves didn't give up because the task was hard. The team that photographed M87 didn't abandon the project because it seemed impossible. But we can pursue knowledge while also accepting that some mysteries might never be fully resolved. We can hold both confidence in what we do know and humility about what we don't. Black holes teach us this balance. They teach us something else too, that the universe is stranger than we imagined, more wonderful, more terrible, more magnificent. 100 years ago, black holes were mathematical curiosities. Most scientists thought they couldn't really exist. The universe wouldn't allow something so absurd. But the universe did allow it. Nature is more imaginative than we are, more daring, more willing to explore the extremes of possibility. And if nature could surprise us this much with black holes, what else is out there? What other wonders exist beyond our current understanding? What impossible things will we discover next?
Why we look up. Throughout this story, we've talked about physics, about mathematics, about vast cosmic scales and incomprehensible time spans. But underneath it all, this has been a human story. It's the story of people, people like you and me, looking up at the night sky and wondering, asking questions, refusing to accept that's just how it is as an answer. It's John Michel, a country rector who could have spent his evenings peacefully reading scripture, but instead chose to grapple with Newton's laws and imagine impossible stars. It's Carl Schwarzschild, calculating in trenches during war, finding beauty in equations while surrounded by death. It's Subramanian Chandrasekhar, a young man facing down the scorn of the scientific establishment because he knew his calculations were right. It's Jocelyn Bell Burnell, who as a graduate student discovered pulsars, rapidly spinning neutron stars that helped us understand stellar collapse, and who faced skepticism and worse, simply because she was a woman in physics. It's Andrea Ghez and Reinhard Genzel, spending decades tracking stars at the galactic center, patient and methodical, building evidence for something they couldn't directly see. It's the LIGO team, who spent decades building detectors sensitive enough to feel space itself vibrate by distances smaller than a proton, and who were proven right when those detectors heard colliding black holes. It's Katie Bauman, who developed the algorithms that turned scattered radio data into the first image of a black hole shadow, and who became briefly the face of that achievement, dealing with both celebration and unfair criticism with grace. It's thousands of scientists whose names we don't know, grad students, postdocs, researchers at universities around the world, people who chose to spend their lives asking questions about the universe, even though the questions are hard and the answers uncertain. This is a story of curiosity, about the human drive to understand. We don't look up at the stars for practical reasons. Understanding black holes won't put food on our tables or cure diseases or solve social problems here on Earth. We look up because we're human, because we wonder, because we can't help ourselves. We look up because somewhere in our evolution, our ancestors developed the ability to ask why, and how, and what if. And that ability, that curse and blessing of curiosity, has led us from caves to telescopes, from wondering about the lights in the sky to understanding nuclear fusion and space-time curvature and event horizons. We look up because the universe is there, vast and strange and beautiful, and we are part of it. We are the universe looking at itself. We are matter that has become conscious, stardust that has learned to wonder. The lonely feeling. There's something lonely about black holes, isn't there? They're cut off, isolated. Nothing that crosses the event horizon can ever return, can ever communicate with the outside universe. They're ultimate prisons, ultimate exile. And maybe that resonates with us. Maybe we see something of ourselves in them. Because we're all a little cut off, aren't we? Each of us lives inside our own perspective, our own consciousness. We can never truly know what it's like to be someone else. We can never perfectly communicate our inner experience. We're all, in a sense, trapped behind our own event horizons. We can send signals out, words, gestures, art, love, but we can never fully cross the boundary between self and other. And yet we try. We reach out. We build telescopes to see farther. We build detectors to hear gravitational waves. We create science not as isolated individuals, but as a community. A global community of people asking questions together, building on each other's work, challenging each other's ideas. We can't escape our individual event horizons, but we can reach toward each other. We can listen. We can try to understand. In studying black holes, these most isolated, most cut-off objects in the universe, we're doing it together. And there's something beautiful about that.
The black hole in our pocket. Let's bring this down to Earth for a moment. Let's think about what black holes mean for us, here, now, in our ordinary lives. You might think they don't mean anything. They're far away, abstract, irrelevant to your daily concerns. But that's not quite true. First, there's the simple fact of wonder. The knowledge that these things exist, that the universe is strange and vast and contains mysteries so deep, can change how you see everything. It can make your everyday problems feel smaller, sure, but it can also make your everyday joys feel more precious. You exist. You're conscious. You're able to understand, at least partially, these cosmic extremes. You're part of a universe that contains both black holes and human consciousness, both the most violent phenomena and the most delicate. That's worth something, worth feeling, worth sitting with. Second, the technology developed to study black holes has practical applications. The algorithms that helped create the Event Horizon Telescope image, they're being used in medical imaging. The same mathematical techniques that reconstruct an image from scattered radio telescope data can help create clearer MRI scans, potentially catching diseases earlier. Gravitational wave detectors required advances in laser technology, vibration isolation, and signal processing. These advances ripple out into other fields. They help us build better instruments for all kinds of measurements. The computer processing required to analyze black hole data has pushed forward our capabilities in data handling, machine learning, and distributed computing. Fundamental research has a way of paying unexpected dividends. We don't study black holes to get better MRI machines, but we get better MRI machines anyway, as a side effect of curiosity. Third, and perhaps most importantly, studying black holes, studying anything in fundamental physics, teaches us how to think. It teaches us to question our assumptions, to follow logic wherever it leads, even to conclusions that seem impossible, to distinguish between what we know and what we merely believe, to change our minds when evidence demands it. These are valuable skills, skills we need in all areas of life, not just physics. The universe doesn't care about our intuitions. It doesn't rearrange itself to make sense to us. Black holes exist whether they seem reasonable or not. Learning to accept this, learning to let reality be the arbiter of truth rather than our preconceptions, is a kind of humility, a kind of wisdom. Looking up together. It's late now. If you're listening to this at night, maybe near bedtime as intended, the world outside is dark. The stars are out, or hidden behind clouds, or washed away by city lights. But they're there. The stars are always there. And among them, invisible, are black holes, scattered through the galaxy, sitting at the centers of galaxies, drifting through space, silent and dark. Right now, at this very moment, somewhere in the universe, a star is collapsing into a black hole. An event horizon is forming. Somewhere else, two black holes are spiraling together, their gravitational waves spreading through space like ripples on a pond. Somewhere, matter is crossing an event horizon, falling toward a singularity, beginning a journey that will never end. It's happening constantly. The universe is dynamic, violent, creative, destructive, all at once. But here on Earth, you're safe. You're far from any black hole, far from their gravity, far from their danger. You can appreciate them from a distance. You can wonder about them.
You can let their strangeness inspire awe, or curiosity, or even a little pleasant fear. The kind of fear you feel on a roller coaster, knowing you're actually safe. You can share this wonder with others. You can tell someone about black holes, about event horizons and singularities, about the photographs we've taken, the waves we've heard. You can look up at the night sky and know that you understand, at least a little bit, what's out there. That you're connected to this vast cosmos, that you're part of the same universe that contains both black holes and human consciousness. That you're made of star stuff, as Carl Sagan said. That every atom in your body was forged in the core of a star, or in the violent explosion of a supernova, or in the first few minutes after the Big Bang. You're connected. You belong. You're part of this. The eternal questions. Will we ever fully understand black holes? Will we develop a theory of quantum gravity that explains the singularity? Will we solve the information paradox? Will we discover whether they connect to other universes, whether they're truly eternal, whether they hold any surprises we haven't yet imagined? Maybe. Maybe not. Science moves forward, but slowly. Each answer raises new questions. Each solved mystery reveals deeper mysteries. But that's okay. The journey is worthwhile even if we never reach a final destination. The questions are valuable even if we never find all the answers. Because asking questions, really asking, really seeking, is what makes us human. It's what gives our lives meaning. It connects us to something larger than ourselves. You don't have to be a physicist to be part of this. You don't have to understand the equations. You just have to wonder. You just have to look up and ask, what is that? How does it work? Why is it there? You just have to care about the answers.